Hi lads. So we're going to have a quick discussion today about the normal shape curve. We talked about this in the last class, so let's go through some of the very basics again. So in a given population, if it's normally distributed, then the mu, the mean of that given population, should lie roughly through the center symmetrically pointed of the distribution. Okay. Now, why is that important? Because it allows it to inform a couple of things about it. Mainly, and this is the main thing, it allows us to employ what's called the empirical rule. And the empirical rule basically states that for any given normally distributed population, where a mu of a mean lies along the middle point, then between mu plus standard deviation and mu minus the standard deviation, you would roughly have 34% either side. For an approximate total of 68% would be covered between plus or minus the standard deviation of the mu. Okay? So it also states that when, sorry, I apologize for the very bad, if we extend this onwards, then between mu and 2 standard deviations and mu minus 2 standard deviations, you would roughly have around there or thereabouts, about 47.5% either side, which gives you a grand total of about 95% coverage. Okay, and to finish it all off, the mu go right out to mu minus 3 standard deviations or mu plus 3 standard deviations. You're roughly talking about either side. I won't get into the numbers, but you're talking about 99.7% of the entire sample would be covered in that. Okay, so this is your empirical rule, and it works as a very good approximation, an extremely good approximation. So there's lots of ways. Once you have some of these details, you can work out a lot of things pretty easily. Okay, now there does lie a certain problem with this, in that first of all, it's an approximation. Okay, we need a far more accurate measurement if we're going to be able to compare different populations. Okay, and for that we use what's called a z-score. A z-score. And the idea of a z-score is it takes the data out of the situation it's in and allows you to compare that data point or that information with other similar data points. So, for example, the easiest one, and probably the one that most people would be familiar with, would be, James gets 62% in his Christmas maths, and he only gets 50% in his Christmas English. Okay, and he arrives home and he says, and Mammy has to look at these, or Daddy has to look at these, or whoever's at home, and says, okay, listen, your maths is not too bad, but your English is woeful. We have to get, seriously, get your act together. And James can say, well, listen, no, come on, look, like the maths class I'm in isn't that strong, so that's quite, that's quite good. And the English class I'm in is like the hardest English class in the world. Or, so he can argue this point, but they're just going to look at those numbers and they're going to say, sorry, listen, 62 is better than 50. So he needs to go away and show them that that 50 is actually brilliant. So what he uses is a z-score, and what a z-score does is it takes it out of that context. So if we look at our original distribution, where we have our mu down the middle, and we know that either side we've got our 34%, and then we've got our 47.5%, and right out. So when we look at those percentages, we can just put them on a scale where 0 is, the closer you are to 0, the closer you are to being average. Okay, and then the more positive you get, the closer you are to being exceptionally good, and consequently, the more negative your number, and so on and so forth, the more further down this tail end you are. So this is a way better scale to be able to do it than trying to work out percentage-wise what percentage do you fall within. Okay, so what's the formula for it? The formula for it is in your log tables, but it's a very simple formula. The z-score for any given data point is that data point minus the mu for that given sample divided by the standard deviation. Okay, and it's a standard score. That's the important thing. This is standardized, so you can compare it against a table and someone else can compare theirs against that table, and you can find out exactly where you are no matter what data set you're looking at. And that's the beauty of this. Okay, so we'll do a little example of one just to kind of make it very easy for yourself. So let's say James, so we'll just scroll down here a little bit, if you don't mind. So let's see, James got 75% in, I don't know, computer science, and James got, let's say, 65% in math. And the question is, we need to figure out some information. So what we know and what his teacher tells James, so he can go home to his mom and explain it to her, is his teacher tells him that the mean mark in computer science was 60%. So that was the mu. And the teacher also said there was a standard deviation of 10. And then his math teacher, who happened to also be his computer science teacher, I wonder who we're talking about here. So his math teacher said, well, you know, the mean in maths was only 50%, and the standard deviation was only 5%. And he was kind of questioning, why do you need this, James? James said, listen, I'm going to need to sort this out at home. Okay, so he goes home and he says, Mom, listen, I'm going to do these out, and this is going to tell you exactly how well I did in both these subjects. So he goes and he takes his science, okay? Or sorry, he takes computer science, and he says, well, my z-score for computer science is going to be that score minus the mean divided by the standard deviation. Okay, so that's 75 minus 60 is 15 divided by 10. That's a 1.5 z-score. Okay, so that's his computer science. That's his comp sci. Okay, let's do a z-score now for his maths. So same thing again. You take your score he got minus the mean divided by 10. Okay, and what you notice, 65 minus is 15. 15 divided by 10 is equal to 1.5. Well, actually, Mom, you might think that I did better in computer science than maths, but I actually did the same in both. Because if you think of the logic of it, the mean in computer science was slightly higher, and he got a slightly bit better. Standard deviation, either side was slightly bit wider. Whereas in computer science or in maths, even though he did slightly less, the mean was also slightly less, and that was also slightly less. So it actually became comparable. So it's quite a very interesting way. Okay, so in both those cases, he had the exact same z-score. Okay, now obviously if he had a higher z-score in one than the other, then he did better, because remember, a higher z-score means you're closer to this end. You're closer to kind of, you know, the H1 end, okay? And a lower z-score and more negative one means you're closer to the NG end, basically, okay? So we're going to get you to try a few of these, okay? I want you to do your best to try a few of these, and we'll have a look at them the next day. All right, thank you.